Hello everyone, welcome back to our channel where we explore essential statistical methods using R programming. Today, we discuss a common dilemma many researchers face, comparing two groups when the data is not normally distributed, which makes the standard t-test unsuitable. Even with data typically expected to follow normal distribution like heights, weights, we often encounter non-normal distributions. In practice, in such cases, the Mann-Whitney U-Test, also known as the Wilcoxon Rank-Sum Test, becomes invaluable. The non-parametric test is crucial when you cannot confirm normality or when working with ordinal data. It's a robust alternative providing reliable analysis without the stringent assumptions required by parametric tests. However, it's important to note that if you know your data is normally distributed, parametric tests like the t-test should be your first choice as they are more precise and valid. From medical sciences to market research, the Mann-Whitney U-Test is versatile. In microbiology, for instance, it has been used effectively to compare the antibacterial effects of different dental adhesive systems. Whether you are examining patient responses, psychological behaviors, environmental conditions or consumer feedbacks, some of those will be a Likert scale, the Mann-Whitney U-Test offer the insights you need. Let's go in R Studio and set up our data and explore how to perform this test in R. Let's discuss the data. Here two groups are there. To one group some treatment is given and performance is measured. To other group that treatment is not given, placebo is provided and performance is measured. Now when we are comparing two groups, the first choice is t-test, and for t-test that data should be normally distributed as we discussed above, and this data is normally distributed or not, we will apply the Shapiro-Test, and Shapiro-Test hypothesis is that the data is normally distributed, or there is no difference between normally distributed data and the observed data. And for that hypothesis, null hypothesis, we will run the test, and this is the output of the test, and p-value is 0.007, 0.008 we approximate that, but it is quite small than 0.05. Therefore, we have to reject the null hypothesis that the data is not different than normal distribution, and we have to accept the alternative hypothesis that the data is normally distributed. Right? We can have other tests also. Kolmogorov-Smirnov test also we can use. Anderson-Darling test also we can use. But here we are going to use that Shapiro-Test. Now, this data I have put into a data frame called as treated and untreated. That data.frame function has been used. I will run that. And now this is the data. This is wide format, and wide format is actually difficult to analyze further, and for that purpose using tidyr functions, library tidyr functions, I will run that. And if you don't have installed this tidyr package, you will get error here, and if you get error that no package is installed, then go to tools, install packages, install that package. Right. Now that data long will be the object in which I will collect the output of this code. Data will be the input. This data will be piped in the pivot longer function, and pivot longer function will collapse those columns, these two columns together in one column. The observations will be there in one column and the category names will be there in other column, and for that purpose these two columns we have to collapse. Therefore, I am giving columns is equal to 1 and 2, 1 to 2. Values to the values, these values will go to a variable called as response. Name of the response variable is there, therefore that is enclosed in a inverted quote, and later on it will become variable, therefore the inverted quote will not be required later. Now we are providing a name that use this name, therefore that inverted quote is there. Names too is there, names of these categories where those names will go. That 540 is the observation treated and 5000 is the observation untreated. Where this will go, these categories will go to a separate column, names too, that is treatment column. And now when we run that, we will have a data. I will just run this code and we will see that, and then see the data long. You can see that treatment is there, treated, untreated, and corresponding observations are there in the column response. Now if you see here, treatment is a character column, and this character column we should convert, because very few categories are getting repeated. Therefore, we should convert that to factor. By using this mutate function, I have converted this treatment to a factor. Treatment is equal to factor treatment. Now, when we run that, and this mutate function is also coming from dplyr, package dplyr, and if you have not installed that dplyr, call the library dplyr. I think I have called that earlier. Therefore, this code is working for me. Okay. Now, for which one I will confirm for which package that mutate function works. That mutate is from dplyr package. I am correct. Therefore, you have to install the package dplyr if you have not installed to run this mutate function. And when I ran this code, we'll see the data again, a small data. Therefore, we can see it completely. Here, instead of character, now it is factor, and this factor has two labels, treated and untreated, and these responses are there. But remember here, the data is not normally distributed. Okay. Therefore, we can't use t-test. We kept that discussion earlier. We have to use Wilcoxon Rank-Sum Test. Wilcoxon Rank-Sum Test. The same test is called as Mann-Whitney U-Test, as we discussed earlier. Now, for this test, the data will be ranked, and then after ranking, the sum of those ranks will be done, and that will be processed to get the statistic W for this one. Before actually applying the test, we'll try to visualize that. Here I actually tried to find out whether those are normal distributed or not. I will run that. The first treated is not normally distributed, and untreated is normally distributed because that is 0.346. Now we will visualize whether these two groups are really different or same using the ggplot. And in ggplot, we have actually called the library ggplot2. ggplot data long will be the input, aesthetics will be X will be treatment, Y will be response, and fill will be treatment. According to treatment, we will get the color. That is not required actually, fill treatment, but we have kept that. Then geom box plot is there, labs and all that. You can study that. I will run to show the plot. So now here visibly it can be seen that treated group performs less as compared to untreated group, and untreated group the values are very high. Now the another one, density also will see. Density plot. In density plot, the X variable is the continuous variable or numeric variable, response variable, and color will be treatment, and actually that other variable is not there. For these responses, density will be calculated, and that will be plotted on the y-axis. Geom density is there. We will run that, and we can see that these two are not at all normally distributed. Here somewhat normal distribution is there for the untreated one, but for treated one, this normal distribution is not possible. Therefore, we can't overlap these two and say that this group is different than that. And for that purpose, we have to apply the non-parametric test or Wilcoxon Rank-Sum Test. Now, here we are there to apply the test. Now, test result will collect here in the object named as test result, and Wilcox.test is the function. Formula interface is there as like t-test. Response is determined by the treatment. In treatment, two categories are there, and we have to compare the response to those two categories. Data is coming from data long. Exact is false. Exact is false because many times ties are there in your data. If ties are there, then you get an error that ties are there and your p-value may not be calculated correctly. For that reason, we are using here the option exact is equal to false. We can remove that also. Initially, we will remove that. Correct is equal to true for continuity correction, because the data is discrete one discretized data, just like that. And the continuity many times may break. Here also that little break in continuity is there. Therefore, to avoid that, correct is equal to true will be kept, and that will run that to see the effect. And here you can see that error in Wilcox.test. Default cannot compute exact p-value with ties, and for that reason we'll remove that exact. We'll keep that exact is equal to false, and we'll run that, and we have the test result. And now we'll get the test result object. Look at that. We have got the object. The test name is there, Wilcoxon Rank-Sum Test with continuity correction. Continuity correction we did using that correct is equal to true. Then data is equal to response by treatment, W statistics is 9.5. This is not the video where I will explain you how to calculate that W, but that W is calculated by comparing the ranks of those two groups. First, the data will be arranged ascending or descending order and will be ranked, normally in ascending order, and it is ranked. And after the ranking, then ranks of group 1 will be separated from ranks of group 2, and it will be tested whether there is consistently high rank in one of the group, if the one of the group is larger than other group, which you can see in this. Here the ranks are quite less, and here the ranks will be little higher, and for that purpose this untreated group will be considered as larger as compared to treated group, and this test actually calculates that only. P value is 0.06. Now this is little more than our alpha. Our alpha is 0.05. Therefore, we have to say that these two groups are statistically not different from each other. Our null hypothesis was these two groups, ranks of these two groups or sum of ranks of these two groups is statistically significantly different from each other. Not different from each other. But null hypothesis was not difference. And here we have to accept that there is difference. There is no difference because P value is 0.06. And no difference conclusion will we have to accept here. If we reduce that alpha to 0.1, then at 0.1 alpha we have to accept that there is difference between these two groups. At 0 we are ready to accept 10% error, but if you are not ready to accept 10% error, if you are ready to accept only 5% of error, then we have to say that these two groups are not different from each other. And true location shift is not equal to 0. Location shift, here you can see the location shift. And actually in this I tried to rank all those, but will not discuss that in this video. The purpose was to compare this with t-test for independent samples. That's all for this session. If you have liked this video, please click the like button, share this video with your friends, and subscribe to my channel if you are not subscribed yet. Thanks for watching.